Good day, everyone. Once again, I am Diana Galieja. Now we're moving forward to Chapter 3, Lesson 4 of our STS subject that concerns about the nano world or the nanotechnology. So let's take a closer look. The objectives in this lesson includes the following: define nanotechnology, characterize nanoscales, describes the various uses of nanotechnology, discuss concerns on the use of nanotechnology, and last, explain the status of the use of nanotechnology in the Philippines. So let me define first what is nanotechnology. Nanotechnology is a field of research and innovation concerned with building things, generally materials and devices on the scale of atoms and molecules. However, a nanometer is 1 billionth of a meter, 10 times the diameter of a hydrogen atom. So the diameter of a human hair is an average of 80,000 nanometers. At such scales, the ordinary rules of physics and chemistry was no longer apply. For instance, materials characteristics such as their color, strength, conductivity, and reactivity can differ substantially between the nanoscales and the macro. So carbon nanotubes are 100 times stronger than steel, but 6 times lighter. So for further explanation, I have here example of video clip to explain more about the nanotechnology.
Hey! Do you know what nano means? It means small, very small. It is 1,000,000 times smaller than the smallest measure on a ruler. If you want to get an idea of how small a nanometer really is, you'll need to take a piece of hair from your head. Go on, it won't hurt. Got it. Now take a good close look at that strand of hair. Not much to look at, is it? If we were to shrink you down, smaller than the smallest thing you can see with the naked eye, you will find that your piece of hair starts to look a lot more interesting. You are now about the size of a red blood cell. Your strand of hair is a massive tree compared to you. Even at this size, you're still about 1,000 times too big to be considered nano. To get you down to the nanoscale, we will have to shrink you to about 100 nanometers tall. Hey, where are all the lights? You are now smaller than the wavelength of visible light. You are practically invisible. But for the sake of demonstration, I think we should turn on some lights. At this size, the red blood cell is 1,000 times bigger than you are. It is like an enormous stadium. Welcome to the nanoscale. You could probably hold a common cold virus in your hands quite comfortably now. The rhinovirus is only about 30 nanometers across and is nearly impossible to see next to the red blood cell. A red blood cell is too big to be considered nano. However, it's made up of all kinds of nanomaterials. If you were to look close enough, you would see that the outer walls of the cell are stabilized by a flexible, mesh-like protein skeleton. The bars and connectors that make up this mesh are considered part of a nanomaterial. Without these reinforcing nanostructures, the cell would be much more fragile and not nearly as flexible. It wouldn't stand a chance in your body. Everything is made up of nanomaterials. Nanomaterials are an arrangement of molecules and atoms that, when combined, create stable building blocks that can be made into larger, more complex materials and structures. Which is pretty much everything, including this little piece of hair. I bet you didn't think there was so much going on in such a small amount of space.
How to view nanomaterials? Scientists use special types of microscope to view minute nanomaterials. So during the early 1930s, scientists used electron microscopes and field microscopes to look at the nanoscale. So we have here the two examples of microscope. The first one is the electron microscope and the second one is the scanning tunneling microscope. So, electron microscope was produced by Ernst Ruska and Max Nall. It is the first electron microscope during the 1930s. So this type of microscope utilizes a particle beam of electrons to light up a specimen and develop well magnified image. So meaning to say, electron microscope produce higher and better resolution than other light microscope because they can magnify objects up to 1,000,000 times, while conventional light microscopes can magnify objects up to 1,500 times only. The next one is the scanning tunneling microscope. Scanning tunneling microscope is a special microscope enables scientists to view and manipulate nanoscale particles, atoms, and small molecules. So the founder of this invention are Gerd Wienig and Heinrich Rohrer. They won the Nobel Prize in Physics because of this invention. So this ends my part. I will give the next discussion to Miss Kyla Marie Villanueva.
Good day, everyone. I'm Kayla Marie Villanueva. Today I'm going to discuss the nanomanufacturing and the distinct features of nanoscale. First, let's have the nanomanufacturing. Nanomanufacturing refers to scaled up, reliable, and cost-effective manufacturing of nanoscale materials, structures, devices, and systems. It also involves research, improvement, and incorporation of processes for the construction of materials. Therefore, nanomanufacturing leads to the development of new products and improved materials. There are two fundamental approaches of nanomanufacturing, either bottom-up or top-down. First, let's have the bottom-up fabrication. It manufactures products by building them up from atomic and molecular scale components. However, this method can be time consuming. Scientists and engineers are still in search for effective ways of putting up together molecular components that self-assemble and from the bottom up to organized structures. Next is the top-down fabrication. It trims down large pieces of materials into nanoscale. This process needs larger amount of materials and discards excess raw materials. So, in bottom-up manufacturing, the process of building products from molecular components, and the top-down nanomanufacturing, the process of developing products from whole piece of material. There are new approaches to the assembly of nanomaterials based from the application of principles and top-down and bottom-up fabrication. This includes the deep pen lithography. It is a method in which the tip of an atomic force microscope is dipped into chemical fluid and then utilized to write on a surface like an old-fashioned ink pen onto paper. Next is the self-assembly. It depicts an approach wherein a set of components joined together to mold an organized structure in the absence of an outside direction. Next is the chemical vapor deposition. It is a procedure wherein chemicals act in response to form very pure high-performance films. Next is the nano-imprint lithography, generating nanoscale attributes by stamping or printing them onto a surface. Next, let's have the molecular beam epitaxy, depositing extremely controlled thin films. Next is the roll-to-roll processing. Roll-to-roll processing is a process where ultra-thin strips of metal in plastic are imprinted with nanoscale devices at a rapid frequency. And the last one is the atomic layer epitaxy. Atomic layer epitaxy is a process where layers comprised of single atom thickness are deposited onto surfaces. So now let's move on to the distinct features of nanoscale. Nanotechnology involves operating at a very small dimension, and it allows scientists to make use of the exceptional optical, chemical, physical, and mechanical and biological qualities of materials of that small scale. Now let's have the first features of nanoscale, which is a scale at which much biology occurs. The second feature is the scale at which quantum effects dominate properties of materials. Now let's move on to the last feature of nanoscale, which is nanoscale materials have a far larger surface areas than similar masses of larger scale materials.
Now, let's proceed to benefits and concerns of using nanotechnology. Nanotechnology has various applications in different sectors of the society and environment. Salamanca Buentello proposed an initiative called Addressing Global Challenges Using Nanotechnology to accelerate the use of nanotechnology to address critical sustainable development challenges. They suggest a model that could help figure out the possible contributions of the community in overcoming global challenges that pose risk on health and other aspects of people's lives. However, there are concerns that need to be addressed before using and promoting materials derived from nanotechnology. First, nanotechnology is not a single technology. It may become pervasive. Nanotechnology refers to the manipulation of matter at the nanoscale, which is the scale of atoms and molecules. It involves creating and using materials, devices, and systems with structures and properties that emerge at the nanoscale. Nanotechnology is not a single technology because it encompasses a wide range of scientific and engineering fields such as physics, chemistry, biology, material science, and engineering. These fields work together to design, create, and control materials and devices at the nanoscale, leading to a vast array of applications across different sectors. Nanotechnology has the potential to become pervasive because it can be applied to almost every field, from medicine and energy to electronics and construction. For instance, in medicine, nanotechnology can be used for targeted drug delivery, tissue engineering, and imaging. In energy, it can be used for efficient solar cells, energy storage, and hydrogen fuel cells. In electronics, it can be used for high-performance transistors, sensors, and displays. In construction, it can be used for self-healing concrete, insulation, and coatings. As nanotechnology continues to advance, it will likely become more integrated into various aspects of our lives, making it a pervasive technology. However, there are also potential risks and ethical concerns associated with the development and use of nanotechnology, such as the impact of the environment and human health. Therefore, it is important to carefully consider and manage the potential benefits and risks of nanotechnology. Second, Nanotechnology seeks to develop new materials with specific properties. One of the key goals of nanotechnology is to develop new materials with specific properties. By manipulating the structure and composition of materials at the nanoscale, researchers can create materials that have unique properties such as increased strength, improved electrical conductivity, enhanced chemical reactivity, and greater resistance to wear and tear. For example, by designing and assembling nanoparticles into specific configurations, scientists can create materials with novel optical properties that are useful for applications in solar cells and sensors. By controlling the size and shape of nanoparticles, researchers can produce materials with enhanced catalytic activity for use in chemical reactions. By altering the surface chemistry of nanoparticles, they can create materials with improved biocompatibility, which is important for medical applications. Overall, nanotechnology offers a powerful tool for developing materials with specific properties, and it has the potential to revolutionize many industries, including medicine, electronics, energy, and manufacturing. Third, nanotechnology may introduce new efficiencies and paradigms which may take some natural resources and current practices and competitive and obsolete. For example, in the energy sector, nanotechnology can be used to improve the efficiency and performance of solar cells and energy storage devices. This could reduce the reliance on fossil fuels and traditional energy sources, making them uncompetitive in the long term. In the manufacturing industry, nanotechnology can be used to develop new materials with enhanced strength, durability, and flexibility. This could make current manufacturing practices and materials obsolete, as nanomaterials can provide superior performance and cost effectiveness. In the agriculture sector, nanotechnology can be used to develop new pesticides and fertilizers that are more efficient and environmentally friendly. This could make traditional farming practices and chemical pesticides and fertilizers uncompetitive. However, it is important to note that while nanotechnology has the potential to disrupt industries and practices, it can also create new opportunities and markets. For example, the development of new nanomaterials and devices could create new jobs and industries and lead to new applications and innovations. And lastly, it may be complicated to detect its presence unless one has the specialist tools of nanotechnology. Nanotechnology deals with materials, devices, and systems that operate at the nanoscale, which is typically between 1 and 100 nanometers in size. At this scale, the properties of materials can be significantly different from those at the microscopic scale, and detecting the presence of nanoscale structures or materials can be challenging. For instance, nanoparticles can be difficult to detect using traditional analytical techniques such as microscopy or spectroscopy because they are much smaller than wavelength of visible light. As a result, specialist tools and techniques are required to observe and analyze nanoscale structures and materials. One example of specialist tools used in nanotechnology is scanning electron microscope, or SEM, which uses a beam of electrons to create images of the surface of materials at high magnification. Another example is atomic force microscopy, or AFM, which uses a sharp probe to scan the surface of materials and create high-resolution images. Overall, detecting the presence of nanoscale materials and structures can be complicated without specialist tools and techniques. However, the development of these tools and techniques has enabled significant progress in the field of nanotechnology, leading to new materials, devices, and applications with the potential to revolutionize various industries and fields. Now, here are the example of areas affected by nanotechnology. What are the possible benefits and what are the possible concerns? So first, for the environment. So the possible benefits would likely to improve the detection and removal of contaminants and the development of benign industrial processes and materials. While for the cons or the concern, we considered here as the high reactivity and toxicity, pervasive distribution in the environment, and no nano-specific EPA regulation. As to the regards of health, it may improve medicine because in the nanoscale, there may be a research that it may also can cure cancer, but for concerns, it may you cause the ability to cross cell membranes and translocate in the body. And moreover, there is no FDA approval needed for cosmetics and supplements, as well as in the areas of economy. For the economy, the benefits would be a better products, new jobs, but the negative here is that there'll be new jobs, but the redistribution of wealth and the potential cost of cleanups and healthcare. So accessibility to all income levels. And now, let's proceed to our last topic, social and ethical considerations in conducting research on nanotechnology. First question. Who will benefit from it? On the other hand, who won't? The second question is, for whom and what are your objectives for developing your product? Third question, how will it affect social, economic, and political relationships? Fourth question, what problem is your product trying to solve? Fifth question is, who will have access to it? Who will be excluded? Sixth, are there dangers involved with its development? Safety, health, pollution? How can you minimize them? And the last question is, who will own it? How can you assure access to it? That's end my part, and I hope you all understand my report. Thank you very much.
For our lesson summary, nanotechnology is an advanced interdisciplinary field that encompasses science and technology that manufactures materials of great help to the improvement of various areas of various society. So it is a field that needs to be explored, and not only by known experts, but also neophytes in order to advance our knowledge of science and technology. So before we engage in nanotechnology, we need to take into account the social, ethical, and environmental concerns for using such nanomaterials.